All right. Ionization, our next subject. So now we've learned a lot, right? We've learned about the structure of atoms, why they have the structure they have, how we can figure out what the electron configurations of atoms are, and we learned about the chemical bonds that atoms can make, specifically covalent and ionic bonds. Okay? So now we need to learn about what circumstances could cause an atom to gain or lose an electron, gaining or losing charge, right? So that word is ionization. So if this is the first time you've heard it, here it is. Ionization is the gain or loss of an orbiting electron by an atom, such that when it loses or gains that electron, a net electric charge is produced. So a neutral happy atom loses an electron. It gets a net positive charge. That's ionization. A neutral happy atom gains an electron and gets a net negative charge. That's ionization. Okay? We've now created an ion. One way to ionize matter is to expose it to electromagnetic radiation. Remember we talked about me jumping up and down off the chair, right? It takes energy to put me up on the chair, and when I jump off the chair, I release energy, right? By making noise when I hit the floor. We learned that electrons are kind of like that, right? Electrons can climb up the ladder, right? But when they fall back down, they don't make noise, they emit photons. And in order to go up the ladder, they'd have to absorb a photon, okay? So let's talk about that. So to be clear, electromagnetic radiation, the particle of electromagnetic radiation is called a photon. Photons can exist at any energy level, okay? Our next lecture will be about photons, okay? But photons are massless and they're a form of energy, okay? They can deposit their energy into an electron. And electrons can lose energy by releasing a photon. Okay? A photon is nothing more or less than a wave in the electric and magnetic field. It's an electromagnetic wave. Okay? Electrons have electric charge and generate a magnetic field. So when an electron moves, it wiggles the electromagnetic field, creating a wave in the electromagnetic field. It's kind of like you guys know like buoys in the ocean, right? You know buoys when the ocean waves come past it, the buoy goes up and down, right? But you could also imagine that if you were big and strong enough, you could go out there and like shake a buoy up and down in the water, right? And make waves in the water, yeah? The buoy is the electron, and the waves in the water is the electromagnetic field. Okay, so the water is the electromagnetic field, and the wave that you made when you shook that buoy up and down in the water, that's a photon. Make sense? Okay, so buoy is the electron, the water is the field, the wave that you created when you shook the buoy, that's a photon, okay? So electrons can create photons by moving. They can also absorb photons and gain energy or gain movement, gain position, okay? It's all about the interaction between electrons orbiting atoms and them either absorbing or emitting photons. In this case, we're talking about absorption. Even though a photon has no mass, so one type of photon is an X-ray photon, okay? It's high energy. It's no different in nature than the visible light we're seeing in this room right now, okay? It's different in energy, though, okay? So an X-ray can carry enough energy which can be deposited into an orbiting electron. That extra energy can give the electron enough energy to where it cannot remain in its shell any longer. It can be raised up out of its shell and ejected from the atom, like we've shown here. A photon comes in from the right, and the electron orbiting absorbs the photon. If it absorbs enough energy, that electron can be ejected from the atom. That's ionization. That's one way of doing ionization. Now, what you've created is this atom will be left behind. By the way, what atom is this? 6 should be carbon. Good. It's the carbon atom. So it's one of your body's atoms, right? Carbon. This atom now has a net charge. With the electron removed from it, what is the net charge of the atom? Positive or negative? Positive charge, right? Because we've removed one negative charge. So now the atom has a charge of +1, okay? So the atom is an ion. What about the electron that went zooming away? What's its charge? Positive or negative? Negative. We know it's -1, right? But it's negative. So the electron that went zooming away, that's a charged particle, or an ion. So now we have two ions that we've created from one event, okay? One's the atom, the other one's the electron. Where'd the photon go?
It could hit something else.
Let's say all of the photon's energy was used in the ejecting of the electron. So where's the photon? It's gone. The photon doesn't exist anymore. It's not matter, remember? Matter exists, right? A photon can be produced and destroyed. It's just a piece of energy, okay? It has all been absorbed into the electron. Okay, the photon is gone now. Its energy is in the electron. There's no mass of the photon left over, so the photon doesn't exist anymore.
I was thinking about it that it can go in.
Yeah, no. If there's leftover energy, the photon can keep on going. You're thinking the right things. I asked a bad question. I didn't ask that very well. But what a point I was trying to get to is there's only now two things left over. Okay, from that event. An electron zooming away over here, and the left behind atom, okay? You have a pair of ions, so you have an ion pair, okay? This ion, so what's important to understand from this is when ionization happens, it's not just the electron that can go zooming around and bump in and cause havoc, okay? That atom you left behind will also now be changed, okay? And it's gonna try to get back to neutral. How is that atom going to get back to neutral? What's it going to have to do?
Steal the electron from another.
And what's that called? Ionic bond, right? Or covalent, right? Depending on exactly what's happening. But the point is that we have an ion, right? So we can form an ionic bond. We can form a covalent bond, okay? It doesn't matter. I don't care about which one right now. But the point is that that atom is now going to make a new bond. What if that atom was already bonded with something? What might happen to that bond? It could be broken, right? What if that bond was one of your DNA molecules? What if it was one of the rungs of your nitrogenous base pairs in your ladder? You now broke your DNA ladder, right? So you can damage things, yeah? If it's a atom in the table, I just don't care, right? But if it's an atom in a living thing, then we might care, especially if that atom is a DNA, a part of the DNA molecule, right? Even if it's water near the DNA molecule, we can create hydrogen peroxide and destroy the DNA by that method, indirect hit, right? So this is a problem. Because X-rays can ionize matter, they can cause harm to matter, okay? So there you are. All right, we're doing good. We're getting close-ish. I want to now talk about I want to talk about nuclear structure now. Sorry, thinking. Nuclear structure. So we've done a lot because what really matters, right, is how the outer shell is configured, how many electrons are in the outer shell, and what happens to that outer shell, right? Is it going to bond? Is it not going to bond? Does it get struck by electromagnetic radiation or not, right? So we now need to go into the nucleus, okay? Good. All right, so some terms. The nucleus has particles, protons and neutrons. Also, parenthetically, you should kind of remember anything that I'm telling you. There's always a deeper level. Okay, the deeper level is that protons and neutrons are actually made of smaller things. Okay, called quarks, okay? Don't worry about that. It's not part of our curriculum, but just remember there's always another level down. This is something that I think is so important to know, is because when we teach you something, if you don't know, it can kind of seem like that's it, right? I've taught you the thing, right? But remember, there's always lower levels than this, okay? This is just a level of explanation that's useful for us, all right? But anyways, the nucleus of an atom has protons and it has neutrons, okay? That's what's there. Remember that most of the mass of an atom is the nucleus. Remember, electrons don't weigh very much. They're not very heavy. They don't have much mass. They have mass, but not a lot, okay? The mass comes from the nucleus. So, these particles in the nucleus are called nucleons. Nucleons include protons and neutrons. As we go up the periodic table to larger and larger atoms, we're of course going to be gaining protons, but we also gain neutrons, and it's not a one-to-one relationship. As we go up the periodic table to bigger and bigger atoms, atoms gain lots more neutrons. So the biggest atoms have way more neutrons than they have protons. For example, hydrogen, atomic number of 1, no neutrons around it. It just doesn't carry neutrons with it, okay? So if you look, so on your periodic table, on any square, just look at hydrogen for now, you notice the top left corner tells you the atomic mass. And in this case, over on that chart, it's the top right corner, you'll notice. But anyways, the number that's just like an integer number with no decimals, that's the atomic number, okay? How many protons there are. But now look at underneath the H in hydrogen, and what's that number say? Like Adrian, what's that number underneath the H?
1.0079.
Excellent. That is what we call the atomic mass. So there's atomic number of protons, but then there's also the atomic mass. The atomic mass is counting everything. Protons, neutrons, and electrons. With all of that together, how heavy is the atom? Okay? So this atom, a hydrogen atom, typically weighs 1.00797 atomic mass units. Meaning, atom of hydrogen is, roughly speaking, just the proton, right? And an orbiting electron. The orbiting electron is where you get the decimals from, okay? The point is that if hydrogen had a neutron, it would have an atomic mass of at least 2. Because remember, the neutrons had an atomic mass of a little bit more than 1, right? So there's no neutrons around hydrogen. You can look at the atomic mass. And so let me give you the trick. If you take the atomic mass, which is at the bottom, and subtract the atomic number from it, that'll tell you how many neutrons are in that atom. Okay? So look at, I don't know, any of these. Just go to helium, okay? Top right. What's the atomic number for helium? 2. What's the atomic mass? 4.0026, right? So take away 2. What's left over? 2.006. So roughly speaking, there's 2 protons in that helium atom. Now, you're going to learn in a little bit that you're going to have atoms of, for example, helium with different numbers of neutrons. We're going to call those isotopes. Okay, I'll come back to that in a minute. What you're seeing right here is on the chart is the most common atomic mass, because atomic masses can change. Atomic number is fixed. Atomic number for helium is always going to be 2, but the atomic mass can be changed by adding or subtracting neutrons. So some examples of how this gets bigger, right? Larger, heavier things like nickel, for example, gets 2 extra neutrons compared to protons. So it has 2 more neutrons than it has protons. But then you look down to uranium. Uranium's 92, and it typically has 92 neutrons plus 54. It has 54 extra neutrons, okay? It has 54 more neutrons than it has protons. And look at uranium. Uranium is going to be found It's called the acidanide series. It's this bottom row. Uranium's right here, fourth one to the right. And just subtract, and I'll do it right here. So the mass for uranium is 238.029. Okay. And the Z number for uranium is 92. Okay, so we'll just take away 92 from that. I'm not going to do this in my head. Put it in my phone. 238.029 minus 92 gives us 146. Okay, there are on average 146 neutrons in uranium, where it only has 92 protons. So these big atoms, they're big because they have so many extra neutrons. Okay, so there's atomic number of protons. There's also atomic mass, total number of things. Interestingly, neutrons neutrons are electrically neutral. So you can add or subtract neutrons all day long, and it's not going to change how the atom behaves chemically. It's just going to change the mass of the atom. Neutrons are neutral, so it doesn't take much energy to hold on to them, which is why you find atoms with many, many, many more of them. And again, atomic mass with this funny little capital A. Okay, atomic mass is not the same thing as atomic weight, but don't worry about that. Atomic mass is telling us, again, how many total particles are in the nucleus. And if you want to know how many neutrons that makes, you just subtract the atomic number from it. And it'll tell you how many neutrons are in there. Now, each element can be found in different forms. So there can be carbon with many different versions of itself. All of these different versions of carbon will have how many protons? Every atom of carbon has what? How many protons? 6. No matter what. All of them have 6. If carbon didn't have 6 protons, it wouldn't be carbon. It would just be something else. Okay? The atomic number of carbon is 6, and it will always be 6. But the atomic mass can change by adding or subtracting neutrons. Each element can be found in different forms based on altering the number of neutrons present in the nucleus. These variations are called isotopes. So now it makes sense when you hear somebody talk about a radioactive isotope. Okay? They're just saying, I've got a radioactive atom, and it's one of the possible options for this atom. We talked about isotopes a little bit when we learned about radioactive decay. If you remember all the way back to radiation safety, we talked about decay and how different isotopes decay differently. Like you learned that uranium-238 has a half-life of like 4 billion years, where uranium-237 or different have half-lives that are like days long or minutes long or whatever. It doesn't matter what the actual numbers are. The point is that something is affected by the atomic mass, number of neutrons, but it's not the chemical behavior. Okay. So common notation to indicate the atomic mass number is in the superscript to the top left or the top right of the elemental abbreviation. So we might see carbon written as carbon 14, for example, written as a C with a 14 in the right superscript or the left superscript above the number. Now, when you see them on the periodic table, usually the atomic mass is put down at the bottom, but it'll always be separate. The atomic mass and atomic number will always be on opposite sides, at least typically. Periodic tables can be set up in different ways. Actually, forget exactly how this one was, but so yeah. So on this one, we put our atomic mass to the top left and our atomic number to the top right. And this is an example showing you here: atomic mass top left, atomic number top right. Don't worry about any of these other numbers; they're not useful for our purposes. Electron configuration. In principle, we could use this, but anyways, the point is that atomic mass and atomic number are different, and they'll be put in different spots. So if I told you, yeah, there's an atom isotope of carbon called carbon 14, you'd know how many neutrons it has, right? Because you know carbon has 6 protons, and there's 14 things in the nucleus of this carbon atom. So take 14 and subtract 6, and you get 8, right? 8 neutrons in carbon, 14 at least. If it was carbon 15, you'd know you'd have 9 neutrons, right? Because there's always going to be 6 protons. All right. So that's what an isotope is. It's an atom of, it's an element, atom of some element, with a different number of neutrons than is typical. Okay? In very large atoms like uranium, these isotopes typically are unstable and therefore radioactive. So isotopes are often radioactive. Do you guys know what carbon-14 is used for? Carbon dating. You guys have probably heard of carbon dating. Is any idea what carbon dating is used for? It's sort of in the word. It's figuring out how old something is. Take some material, I pulled some fossil out of the ground, right? How old is it? We can carbon date it by looking at the radioactivity of carbon-14. And we know the half-life of carbon-14, so we can look at how radioactive it is. When we know its half-life, how radioactive it is, we know how long it's been in the ground for. Okay, we can learn how old something is by looking at the radioactivity of some radioactive isotope that is in it. For example, carbon-14. Good. All right. Next term, nuclear fission. Okay. Now we said that an element is the smallest unit. Let me rephrase that. We said that an atom is the smallest unit of an element that retains all of the chemical properties, right? So if you take an atom and split it apart, then it's not going to act the same as that atom originally did, right? If you take helium, which has an atomic number of 2, and you split it into 2 pieces, what have you now made? You made 2 hydrogen atoms, right? So you took helium and broke it apart. 1 proton over here, 1 proton over here. Ignore the neutrons for now. Proton over here, right? And electrons will go with it. Okay, so now you made 2 hydrogen atoms. You have done a fission to helium. You've fizzed helium. Okay, so nuclear fission is the splitting of an atomic nucleus into smaller fragments. This is what radioactive atoms do. They undergo nuclear fission spontaneously. Okay, they break apart. When they break apart, so when I just in that example, when I broke helium apart, did it stay as helium? I didn't get half a helium over here and half a helium over here, right? It changed all of a sudden now. I went from having helium to now having 2 hydrogen atoms, yeah? So I don't have the same element anymore, okay? We call this transmutation. When atoms undergo fission, they transmutate. They change into something else because they're going to act chemically different, right? Helium acts one way. Hydrogen acts a completely different way, right? And I took one and made the other from it. So in fission, we transmutate atoms into different, then they have different properties after the event. Whatever atom this was before, these 2 new atoms are going to be different. In nuclear reactors, this must be done with extremely high-speed neutrons to overcome the nuclear binding energy, but the point is that we use this. When you split atoms apart, you release energy. Think back to what I was talking about earlier when I showed you all the common elements in the universe. I told you hydrogen's the most abundant element in the universe, right? How did we get helium? Exactly. Does that just happen? What does it take to fuse 2 hydrogen atoms together? A lot of energy, right? So, if it takes energy to put them together, what's going to happen when you break them apart? It's going to release the energy, right? Energy's conserved, right? If we used energy to put them together, That energy didn't disappear. It's in the fusion of the atoms. So if you take an atom and it breaks apart, you release energy from that interaction. If you take this and do this in the nuclear reactor, you release energy. You can use that energy to boil water. You can use that boiling water to have steam, and you can use that steam to spin the turbines to make electricity. So in nuclear reactors, we're literally just boiling water to spin a turbine to make electricity, okay? The nuclear part of it is just getting the heat. It's just where we get the energy from, okay? But that's fission. So now, fission releases energy. Interestingly, certain atoms, if you fuse them, that releases energy. It takes energy to put them together, but there's energy released more than what you put in when you fuse certain atoms together. Like when the sun fuses hydrogen to make helium, it takes energy to do that fusion, but once you do it, you actually get more energy back out.
Where does the neutron come from?
Where does it come from?
If you're fusing two hydrogens and have no neutrons.
Yeah, so protons fuse with electrons. For one, helium doesn't have to have neutrons. That's one isotope of helium. So there's a better answer, there's a longer answer to that, but it doesn't have to have the neutrons. You can just fuse and make helium, just pure 2 proton, 2 electrons orbiting. That's helium, but it can have isotopes that have neutrons. Yeah, the first fusion events didn't give us that. They gave us the pure forms of helium, just two protons, 2 protons, 2 electrons. No neutrons in that case. So check this out. Helium gets made from fusing hydrogen, but our sun goes another step further, and even more steps after this, right? You can take 3 helium nuclei, each of them has 2 protons each, right? Take 3 of them, you fuse those together, and you've made carbon, okay? Our sun right now is fusing helium into carbon. How did we get all of our carbon? Well, some suns before us blew up and spread that carbon around the universe, right? And some of it ended up in in the Earth, and well, that's where we came from. So extreme energies are required to fuse things, but once you do it, in some cases, any atom smaller than iron, if you fuse any 2 atoms smaller and make something smaller than iron, you get energy out. You get free energy from fusing them. So you get more energy out than you put in, okay? But once you get to iron, once you start to try to fuse that into bigger things, it actually takes more energy to fuse it than you get out. So you start to lose energy. This is why suns die. Okay, you know that like the lifetime of a sun isn't infinite, right? Our sun's going to live for like 10 billion years total. We're about halfway through right now, about 4.5 billion years into the sun's lifespan. It's going to live for about another 4.5, 5 billion years. It's going to die once it runs out of things to fuse. Fusion gives us free energy, but you're going to run out of it eventually. You're going to run out of things to fuse. And so once our sun starts to try to fuse iron into 2 iron atoms together, it's going to start to lose energy and stop being able to be this self-perpetuating process. Okay, so it's going to die. 5 billion years. We got time though, right? We have 5 billion years to figure out how to get out of the solar system into another sun. But there you go. So here's the deal. Both fission and fusion result in the release of energy, and result in the release of very large amounts of energy. Fission, we use all the time, okay? All power plants right now that are nuclear work with fusion. We would like to develop, let me rephrase it. All power plants right now that work with fission. I think I said that wrong. We would like to create nuclear fusion. Now, if you pay any attention to like popular science, you know we can do it, okay? They have, in special circumstances, created fusion. Okay, like a mini sun, all right? But it takes so much energy to do it that currently we're not getting as much energy out as we're putting in. Okay, so it's still too much of an energy-intensive process. And but the great thing about it is, like, unlike fission, when fission's done, like you take some radioactive elements and you let them undergo nuclear fission for some time, then eventually they're like done undergoing fission, and you have to take that nuclear element and you have to take it out to, like, I think it's the Nevada desert or whatever, and bury it deep underground where they have the nuclear waste storage, right? And it just stays there for forever, radioactive for forever. Fission produces no waste. Okay, sorry, fusion, gosh. Fusion produces no waste, okay? Taking and fusing two lighter atoms together releases energy with no waste product from it, okay? Fusion's a clean way to make sustainable energy. It's just that it's hard, is the point. Our sun does it all the time, but the sun is extremely high energy, a bunch of different things about the sun that make it able to do that. We can do fusion, but it's hard. So, but that's the deal, right? The point is that there's energy in fusion. All right, let's finish this with some more stuff. We got a little bit more to talk about. I want to talk a little bit about radioactivity, which it's important to know, but most of what we do is not radioactivity. Most of what we talk about is ionization due to electromagnetic radiation. Remember, X-rays, right? So let's talk about radioactivity a little bit. So first of all, you need to understand that atoms would like to be stable, okay? But some atoms are not stable. Stability has to do with the number of protons and neutrons that an atom has. When an atom gets especially large, it can be unstable. An atom will always try to seek its ground state. This is the state at which an atom is at its lowest energy position. An atomic nucleus is at its lowest energy state when it's in its ground state. All nuclei would like to be in their ground state, the lowest energy states. The ground state for a nucleus of an atom is defined by the most ideal number of neutrons for that element. If there are too many neutrons or too few neutrons, the atom can be unstable. That instability manifests itself in radioactivity. Unstable atoms tend to get more stable by breaking apart. So they release excess energy in the form of radiation. This radiation can either be particles, as in the atom is literally breaking apart and shooting off parts of itself, or in the form of electromagnetic waves like gamma rays. So now that you have the ground state idea, let's get some definitions. Radionuclide, any atom that's radioactive. So uranium, radionuclide. Potassium-40, it's a radionuclide. Isotope, any atom with an unusual number of neutrons for that element. Isotopes do not have to be radioactive, but there are plenty of radioactive isotopes. We call them radioisotopes if they're radioactive ones. So that's any atom which is radioactive because of too few or too many neutrons. Any number different from the usual number is not necessarily too few or too many. There's a range of stability for each element. It gets kind of complicated, so we don't talk about it very specifically. But let me give you a toy, simple example, one that you can easily remember, because you already know what hydrogen's all about, okay? You know the atomic number for hydrogen, you know the atomic mass for hydrogen, you can tell me how many protons are there, and you can tell me the electron configuration for hydrogen because it's the easy one, right? One of each, okay? Hydrogen typically has no neutrons. However, there are isotopes of hydrogen called deuterium and tritium. Now, deuterium, which is hydrogen plus a neutron in the nucleus, not radioactive. It's an isotope, but it's not a radioisotope. However, tritium, 2 neutrons, 1 proton. So now there's an imbalance, right? We've got more neutrons than protons. Tritium is radioactive, so we call it a radionuclide. It's also an isotope of hydrogen, so we call it a radioisotope too. Both terms are appropriate. Not one or the other, but both. Tritium is a radionuclide. It is radioactive because 2 neutrons is too many for hydrogen's nuclear binding energy to hang on to. So what is tritium going to have to do? How is it going to get to its ground state? It's going to have to shoot out that neutron or convert that neutron into a proton and electron, giving off a beta ray. Or it's going to have to emit gamma radiation. It's going to have to do something to shake off that extra energy, okay? We don't care right now. By the way, I'm not going to give you the answer to what tritium's going to do, but tritium's going to have to do something to shake off that extra energy. Does anyone know where we use tritium, like in everyday objects? It's used as a glow-in-the-dark, but it's not the kind of glow-in-the-dark that you have to hold up to light. If you have a tritium, for example, like a watch dial that has tritium, it will always glow because it's radioactive, right? It's not the point, but it's also not radioactive enough to like be harmful. It's radioactive, but enough to like emit visible light. Okay, so we use tritium on watch dials. If you never want your watch dial to fade, you always want it to be able to glow in the dark. It'll fade after like 10 or 20 years, but it never fades in the short term. We use tritium, so like for weapon sights, like the sights on a weapon. Okay, you know, like a gun or something like that will have a front sight and a back sight that you line up to aim at your target, right? Well, they'll use tritium as one of the sights, and you can actually see that at nighttime. So for shooting at night, sometimes we need, think military and police applications, right? You don't want to use a light on your weapon. You want to be able to line up for your sight, so they use a piece of tritium in there. Okay, tritium's great. Tritium's a nice little element because it's always glowing in the dark. It's always glowing. Okay. Because it's radioactive. Again, small amounts of radioactivity, so it's safe to put in things and wear on your watch and things on your watch dials and things like that. What did we used to use as a radioactive element on watch dials? Remember it from radiation safety? Radium. Radium, yeah. Radium was a radioactive element that was painted onto watch dials to make them glow in the dark, and it always glowed in the dark like tritium did, but it's very radioactive. And the people that painted the radium onto the watch dials were always women, and they would take and lick the tip of their brush to remember that to make the brush tip pointy, and so they could make a nice little fine line. And they got like bone cancer from it. Like hundreds of them got bone cancer from ingesting radioactive particles all the time. So there are things that are, of course, radioactive and unsafe, but tritium's kind of a safe one. Anyways, moving on. More definitions for you. When I say decay or radioactive decay or decay event, this is any time a radioactive element loses mass or energy from the nucleus. Okay, so up there in the lights is some gas in these fluorescent bulbs, okay? And right now we're running electric current through that gas in those bulbs, okay? So electricity is going from one end to the other. It's exciting the atoms and making the electrons wiggle around. When electrons wiggle, they emit light, right? So, is that radioactive decay? Electrons wiggling and emitting visible light. No. I'm sorry. You guys are doing good, right? So, but why isn't it radioactive decay? It's energy leaving an atom. Where's the energy coming from? This is what the point is what I'm trying to get to. Where's the energy coming from? Yes, but think about an individual atom up there in that gas, right? The light is coming out of the electrons, okay? Electrons in the atom are wiggling around, emitting light, okay? So is the energy coming from the nucleus of the atom up there or the electrons orbiting? The light that we're seeing. Is it coming from the nucleus or the orbiting electrons? The orbiting electrons, right? And how did we define radioactive decay?
Mass or energy
lost
yeah.
from the nucleus, right? So that's not radioactive decay because it's not the nucleus emitting excess energy. Energy is leaving those atoms and coming to us in the form of visible light and also heat. Like if you go up there, it's hot, right? But it's not coming from the nucleus. If the energy is released from the nucleus of an atom, we call it radioactive decay, okay? Decay events happen when a nucleus of an atom loses energy. That energy loss can be in the form of mass or photons, or both, okay? But importantly, it's coming from the nucleus. Radioactive atoms are radioactive because of what their nucleus is doing, not what the orbiting electrons are doing, okay? When a decay event happens, if it's the right kind of decay, an atom can change its identity. Atoms can move up or down on the periodic table when they decay. This is called transmutation. This happens because certain decay events change the number of protons in an atom. What number did we learn today represents the number of protons? The Z number, or atomic number, right? And that atomic number is special to each element, right? Carbon's got 6, oxygen's got 8. Do any other atoms have an atomic number of 8 besides oxygen? No, right? So if oxygen gained a 1, it'd be whatever's after oxygen, right? You can tell me, it's not that important to me. But the point is that if it changes that number by changing the number of protons up or down, it's a different thing now, okay? It's going to behave differently. So let's look at these possible types of decay events and what they do to the atom. And if you've been with radiation safety, you've heard some of these. So alpha radiation. Alpha, also called alpha rays or alpha particles. Alpha particles are a helium nucleus. See it? 2 protons, 2 neutrons, helium nucleus. But that's what an alpha particle is. An unstable atom over here fires off a helium nucleus to get more stable. This is the decay. Now, the number of times per minute or second or whatever, how often it does this, is the radioactivity of the atom. That's what we learned back in safety. We don't need to do that right now. What has this nucleus lost? Protons and neutrons. How has its atomic number changed? It lost, well, think of atomic number first. You're right, but think of atomic number first. It lost protons. How many of them? 2. So what can we say? We can say that whatever this atom was, it's now shifted down 2 blocks on the periodic table. Okay? You know, this could be anything. I don't even care. Let's make up something. Let's say that it is titanium. Okay, titanium 81. Okay? Well, I don't like that because I don't know what the next one down is. Let's go over here. Let me go over here.
Gold, that's 79.
79 is gold. Oh, yeah, 79 is gold. Duh. AU. Okay, so yeah, you come down and you shift to whatever the next thing down is. Okay? That's given by an alpha particle. So now we lost 2 protons, right? So we transmutated 2 down, whatever on the periodic table, doesn't matter what it is, it's gone 2 down on the table. We've lost atomic number 2. What happened to our atomic mass? Down by 4, right? So we got a lot lighter. We lost 4 pieces, but our atomic number only shifted by 2. An example given here is, this is a normal decay process, transmutation process. Radium of 90 goes to radon of 88 by emitting an alpha particle. Elements can do a whole series of transmutations until they get stable. Remember, the whole goal is to get stable, right? So uranium emits an alpha particle and goes to thorium. Thorium is radioactive, so thorium goes to radium. There's your radium, the watch dials, okay? Radium of 88, another alpha emission, turns into radon. Remember, radon's that gas that builds up in your basements. Radon of 86 goes to polonium of 84. Polonium's in cigarettes. Polonium goes to lead, 82, okay? And lead's stable. So after lead, so here's what you need to know about lead. This is worthwhile remembering. Lead is the largest stable element. Lead's not radioactive. It's the biggest element. Let me rephrase that a little bit. It's the largest naturally occurring element that is stable. So yeah, uranium keeps transmutating, turning into different stuff until it gets to lead, and then it stops because it's happy. Now, it doesn't have to go uranium, thorium, radium, radon, polonium, lead. It can go in whatever order depending on the type of emission. Sometimes the emission is a beta emission, in which case it gains a proton. Okay? But right now I'm just giving you the alpha emission version of this where it loses 2 each time. So yeah, the next one is beta. Beta emissions are kind of funny. Beta emissions are take a neutron and let it split up. Remember, a neutron was really a proton and an electron, okay? So let it decay into those two things. Because the electron is so light, it gets shot away from the atom, and what's left behind is the proton. So you turned a neutron with 0 charge into a proton and an electron pair, okay? And you left behind the proton, which adds 1 proton now. So now you're transmutating up the periodic table instead of down, okay? Notice the atom didn't get heavier, it actually got lighter. But so its mass went down a little bit, it went down by 1 electron, okay? But its number went up. Let's give an example. Hydrogen, well, it'd have to be deuterium, but whatever. So isotope of hydrogen is deuterium. 1 proton, 1 neutron. We talked about that one when we talked about tritium, right? So you take hydrogen as an isotope, deuterium. So deuterium is just hydrogen with 1 extra neutron, okay? That extra neutron happens to decay, okay? And what's it going to turn into? Well, let's do the tritium one, okay? Tritium. So hydrogen as an isotope, tritium, okay? 2 extra neutrons. We said that's radioactive, so it undergoes a beta emission, okay? You turned a hydrogen atom with 2 neutrons into a helium atom with 2 protons, 1 neutron. So you converted one of the neutrons into a proton. And what flew away was the beta emission, was this little beta particle, okay? That turned hydrogen into helium without fusing anything. A radioactive decay event turned hydrogen into helium. We went up the periodic table by converting one of tritium's neutrons into a proton. That happens because tritium's unstable, so it becomes helium-3. Helium-3 is just telling us we have helium plus one more thing, and that's a neutron. And that's more stable. So one thing too to remember is that atoms always want to get to their ground state, their most stable state. If the most stable state is going from tritium to helium-3, then that's the way it'll go. It will never go the opposite direction. Atoms will never become more radioactive over time. There is only it's like leaving a battery on a counter and it just spontaneously charging itself, right? It's not going to happen, right? Batteries die when you leave them alone. Atoms decay downward in energy, okay? It's just part of the process. So with time, the atoms will decay downward in energy. Helium-3 happens to be more stable than tritium. The last emission is called a gamma emission or gamma ray. Gamma rays are interesting. So let me give you some stuff about gamma rays. Gamma rays come from moderately unstable nuclei. Normally, when electromagnetic radiation is emitted, it's coming from electrons, right? We've talked a lot about electrons emitting electromagnetic waves, creating electromagnetic waves. That's what a gamma ray is. It's an electromagnetic wave like an X-ray. It's actually almost the same in energy as an X-ray. The only difference is where it comes from. X-rays come from orbiting electrons. Gamma rays come from unstable nuclei. This emission lets the nucleus lose a little energy, getting more stable, but interestingly doesn't change the atomic number and doesn't change the atomic mass, because we haven't lost any mass, right? We didn't gain or lose a proton, so our atomic number can't change. We didn't gain or lose any mass because we emitted a massless particle. So we just lost energy. So moderately unstable nuclei. When do gamma emissions happen? They typically happen after alpha emissions. So an atom is really unstable, shoots off a big piece of itself, and now is only a little unstable. So gamma emissions, the next likely thing. After the alpha particle escapes, slightly more energy is left. That energy is emitted as as a gamma ray, excuse me. Okay, so you have all three. And by the way, all three happen, and we're not telling you in exactly what order they happen or when they happen, what circumstances they happen, but all three things, alpha, beta, and gamma emissions, happen in unstable atoms. Atoms are unstable when they're larger than typical, okay? They're larger than typical, that means there's extra neutrons, and atoms shake off extra particles or energy to get to a more stable state. And that, my friends, is the end of today's stuff, okay? We have covered quite a lot today, lots to think about, and next time we're gonna take all of this that we learned, the matter talk, and we're gonna do our energy talk, okay? We're gonna squish all that together, okay? Thank you guys.